I believe going by the last lecture, we have seen the reason why oxidation and reduction reactions are very, very important, both in the layman understanding and the scientific view of it. It is based on that we are now presenting a concluding part of that topic, oxidation and reduction reaction second. That is the name. Our learning objective by our usual practice before we start any class is to define what our learning objective is, so that after the end of the class we should be able to assess ourselves if we have really met those set objectives or not. We have defined oxidation and reduction at least in 4 different respects. The first one in terms of oxygen, another one is in terms of hydrogen. We have talked about electron transfer. We talked about the electronegativity and electropositivity. Those are the 4 or 5 ways we have defined oxidation and reduction, and we have identified oxidation. As in a chemical reaction, we have identified oxidation, we have identified reduction, and we have made us to realize, to understand that one cannot happen independently of the other. Both of them are going together. If oxidation takes place in a particular reaction, no matter how simple or complex that reaction is, oxidation takes place, reduction also takes place in that reaction. That was our understanding in the last class. Another understanding again is, if you are balancing redox reaction, you have to balance each of the half reactions independently, but the number of electrons lost in oxidation must be our guide as to how we are going to balance the 2 reactions, simply because the number of electrons is what we want to use to balance them ionically. If the number of electrons in each of the half reactions, half equations, are not equal, we have to make them equal by just manipulating the figures. Maybe we put the LCM of the number they output, or just multiply them by some factors. After doing that, we add the 2 equations together, the reactant to the reactant, product to the product. We will see that electron will cancel out each other. That was what we learned last class. So today we want to go to another concept of oxidation reduction. Today in terms of oxidation number. What is oxidation number? How can we use it in the definition of our oxidation reduction? How do we calculate oxidation number? Because without knowing how to calculate the oxidation number, simple rules that are followed, we will not be able to understand fully how oxidation number is used in defining oxidation reduction. And again, identification of redox species in a particular reaction is very, very important, although we talked about it briefly in the last lecture. How do we know this one has oxidized, this one has reduced? Apart from the transfer of electron, apart from hydrogen electronegativity that we said, so we can actually and reliably use the knowledge of oxidation number to know which of the substances has oxidized, which of them has reduced, and what causes the oxidation. Another one is distinction between oxidizing and reducing agent in a particular reaction. We say that reduction and oxidation takes place together, but if there is oxidation, what causes the oxidation? If there is reduction, what causes the reduction? So all the other substances that cause the oxidation reduction, they are what is called oxidizing and reducing agents. How do we distinguish them, and how do we identify them in a reaction? And the last but not least is the application of oxidation number in naming inorganic compounds. This concept is very, very important because without knowing it, naming compounds will not be easy, especially compounds that are not simple like sodium chloride. All those ones are simple. Magnesium chloride are simple. But when it comes to tetrasulfate 6 acid, heptatose dichromate 5, so all those things, how do we get 6, how do we get 5, how do we get 3? So it is the knowledge of the oxidation number that is actually employed here. So let us go. What does oxidation state mean? It is just a way of telling us the movement of electrons, how electrons are shared, how they are transferred in a reaction. We should not forget that we said in a chemical reaction, it is either electron is transferred or electron is shared. We have talked about that times without number. So it is that oxidation state now that now tells us which direction electron will go. Is it going to be lost or gained or shared when the compound is being formed? So that now helps us to identify the redox reaction, apart from other identification that we have talked about. So there are some rules that are followed in writing the oxidation state, guiding us how to calculate the oxidation state. Number 1 is each atom in the formula has an oxidation state. When you have a formula, a chemical compound, let's say sodium chloride, potassium chloride, magnesium hydroxide, each of the atoms that are in each of those formulas, they have oxidation state. And also the oxidation state is usually given as a Roman numeral, like 1, like 2, like 3 in Roman numeral, not like we have written it. I mean 1 is like high, 2 means high high, 3 means high high high, 4 is IV, like that. Where an element is not combined with other elements, its atom are in oxidation state of 0. What we are saying is this: element in its elemental state has an oxidation state of 0, oxidation number of 0. I mean, if sodium, we are in sodium chloride now, rule number 1 has taken care of that each of them has an oxidation state. But if sodium now is now solidly or appearing like sodium, potassium is potassium, calcium is calcium without attaching itself to other elements, the oxidation state in that respect, in that particular period, is equal to 0, no matter the element it is concerned. Then the last one is in any formula, number 4, in any formula, the oxidation state must add up to 0. What this means is this: you have a formula, let's say sodium chloride, let's say HCl now, let's say HNO3 now. So the oxidation state of each of the elements that are combined together must be equal to 0. I mean, if take sodium chloride as an example now, the oxidation state of sodium, if we add it to that of chlorine, must give us 0. If we take HNO3 as an example, the oxidation state of hydrogen together with that of nitrogen together with that of oxygen, if we add them together, they must give us 0. Many elements have the same oxidation state in most or all their compounds. This table will guide us. What we mean by that is this: there are some elements that their oxidation states are constant, especially metals in group 1 and group 2, and again non-metals in group 7. Aluminium also has constant oxidation state. But elements like hydrogen, sometimes it change, but not every time. Majority of the time, the oxidation state is usually +1. So in some cases, like in hydride, as in when hydrogen now reacts with a metal to form hydride, like sodium hydride, potassium hydride, calcium hydride, that is when the oxidation state now change, because metal is more stable. So oxidation state of metal remains as it is. Or the group 1, there's no condition that will make the oxidation state of sodium not to be equal to +1. It has to be +1 all the time. So if there's going to be an oxidation state that is going to change, it's going to be the element that attaches itself to sodium or to chlorine. To sodium or to potassium or calcium, or those metals in those two groups. The last one is the atoms of transition elements can have variable oxidation state. In fact, that is one of their properties, that the transition elements, they have variable oxidation state. Like iron now, iron can present itself in oxidation state of 2 and 3. Chromium can have 3, can have 6. Manganese can have 2, 4, 7. Copper can have 1 and 2, as the case may be. So all these elements are transition elements. So anytime they are involved in a particular compound, the oxidation state must be clearly stated, so as to know the state of which they are when they reacted. That is that. So let us now employ those rules, or those 5 rules, to calculate oxidation state. In magnesium chloride compound, the first rule is that all the oxidation state in a compound must be added to 0. Magnesium, from this table now, group 2 element, magnesium has a +2, chlorine has -1. So that is in most of the cases. So -1. So this is +2 for magnesium, this is -1 for chlorine, but we have 2 chloride atoms here. So if you add this together, you go to 0. So that one has proved this. Number 4, it has proved it to be correct. That is the first one. So having proved that number 4 to be correct now, so we now apply that to solve our problem here. Calculate the oxidation state of sulfur in H2SO4. Our hydrogen is +1. Our oxygen is usually -2, except in peroxide when it is -1. So our oxygen is -2. So let us now put them here now. We have 2 atoms of hydrogen, we have 4 atoms of oxygen. So if we look at that, then everything must be equal to 0. We have our S to be equal to +6. That is why it is being named tetra also sulfate 6 acid. That 6 is coming from the oxidation state of sulfur. I believe you have understood that now. So having understood that, calculate the oxidation state of manganese in this case. Don't forget, we have said manganese can be 2, can be 4, can be 7. I'm not telling you to cram all these tables. It's just to give you a guide. So if you calculate the oxidation state of manganese, this is a group 1 element, potassium, you have +1. This is a non-metal, that's a deficit of 2, that is -2. So Mn that you don't know, call it Mn. So you multiply this one by 4, that is -8. -8 plus 1, that is -7. So if you put -7 to the other side of the equation, because everything must be equal to 0, so you have +7. That is why this compound is called tetraosomanganate 7. So that 7 is coming from the oxidation state of manganese. So now, in a redox reaction, how does oxidation state change? Because we have said that we want to use this change in oxidation number, oxidation state, to determine oxidation reduction. So we want to know how it changes. Consider this reaction. Sodium reacting with chlorine to form sodium chloride. Before the reaction, sodium was in elemental state. Oxidation state must be equal to 0, law 3. Chlorine was in elemental state. Elemental state means it is not reacting with anything, it is just ordinary. So chlorine has 0. After the reaction, so let us assume that we know the oxidation number of chlorine now. We want to calculate that for sodium. Chlorine is -1 because it is a group 7 element -1. That is valence electron. So if we have sodium, then -1 is equal to 0 because everything must be equal to 0. So sodium will now have a +1. So having known the number of sodium now, we want to calculate the number of chlorine now. Let us assume we don't know it. So we have sodium to be +1, then calculate that. So we have chlorine to be -1. Oh, sorry, this is chlorine, not oxygen. -1. So it means sodium has lost 1 electron. And again, from our second definition of oxidation, electron transfer, loss of electron means oxidation. So sodium has lost 1 electron, so it has oxidized, while chlorine has gained an electron, therefore it has reduced. So can we now transfer that to change in oxidation number to define redox? Yes, we can do that. And again, to remember this, oil rig means oxidation is loss of electron, reduction is gain of electron. So just get this oil rig so you will not be confused when you see oxidation and reduction. Note, if oxidation state change during a reaction, it is a redox reaction. If it doesn't change, it is not a redox. That is the meaning. For you to consider a reaction as being a redox, then oxidation state must have changed in that reaction. Now, in terms of oxidation state, how do we define oxidation? Oxidation is defined as a process that involves increase in oxidation state. We have seen it here. Sodium has increased from 0 to +1. That is, we said that's oxidized based on electron transfer. So we have linked electron transfer to oxidation state now. So it has increased. Then for chlorine, it has reduced from 0 to -1. So it has reduced. So reduction is decrease in oxidation state. That is just where we are going. I mean in terms of definition, not for today's lecture. I believe you don't have any problem with assimilating those concepts. So if there is any problem, let us go back to the last class and see where there is problem and try to face it. So another concept we are going is the concept of oxidizing and reducing agent. We are familiar with this reaction when copper sulfate is being reduced by hydrogen to form copper and water. And we have established that copper sulfate is reduced to copper by reaction with hydrogen. So what reduces the copper? This hydrogen. So hydrogen serves as the agent to reduce that copper. So hydrogen is the reducing agent. Let me repeat myself. We have established before that when there is loss of oxygen, there is reduction. So in this case, copper oxide has been reduced to copper because oxygen has lost. But what removed the oxygen from it is hydrogen. So hydrogen has caused copper oxide to reduce. Then the name given to hydrogen that serve as agent to reduce copper oxide is called the reducing agent, because it is the agent now, it is the substance now that causes the copper oxide to be reduced. The hydrogen in itself is oxidized to water because before it was hydrogen and now water has been added. So addition of oxygen is oxidation. So hydrogen has been oxidized to water in reaction. So in that case, what caused the hydrogen to be oxidized? It is copper oxide because it has transferred oxygen to hydrogen to make it water. So copper oxide is an oxidizing agent. What are we trying to say in this? Since oxidation and reduction must take place simultaneously, it means any substance that is oxidized is a reducing agent. Any substance that is reduced is an oxidizing agent. It is like that. Any oxidizing agent oxidizes another substance. So in that case, it itself it has reduced. Then reducing agent itself is oxidized because that's reduced another substance, so itself is oxidized. So let's have examples of oxidizing agents, because sometimes some substances are just oxidizing agents, that they are not reduced. Some are reducing agents, but some depend on reaction to which they are involved that will serve as if it will be oxidizing agent or reducing agent. Potassium dichromate 6. It's a very strong oxidizing agent in which the presence of acid, if it reacts, it gains electron. If it gains electron, that means it's oxidized. It's reduced. That's what we're saying. So if it's reduced, that means the other substance that might have transferred the electron to this potassium dichromate will have been oxidized. That means potassium dichromate 6 has served as an oxidizing agent. Before, the oxidation state of the chromium used to be 6. So now when doing this reaction like this, it changes to 3. So the color will change, showing that the reaction has taken place. So that color change from orange to green is an example of how potassium dichromate 6 change during a reaction. Another one is permanganate, potassium permanganate. If it takes electron from other substances, it reduces and color change from purple to colorless. So potassium permanganate, it used to be 7 before reaction. So during this reaction now, that's 7 oxidation state of permanganate is purple in color. During reaction now, the oxidation state now changes to 2 because it usually accepts 5 electrons. So if it accepts 5 electrons, oxidation changes to 2. That manganate 2 at 2 oxidation state is usually colorless. So that will tell us that reaction has taken place. So let's go to reducing agents. The list is not limited to that, but let us just get that concept and go to reducing agents. Potassium iodide. When potassium iodide solution is added to hydrogen peroxide, also in the presence of acid, there's going to be this reaction. So this carbon of contention is potassium iodide and hydrogen peroxide. Those are the two main players. This H2SO4 just acts as an agent that makes this reaction possible. So after the reaction, what happens to the iodine? It has lost potassium. What happens to hydrogen peroxide? It has lost oxygen. So hydrogen peroxide has lost oxygen, that means it has reduced. If it has reduced, it's an oxidizing agent. So to add to our list here, you can put hydrogen peroxide as an oxidizing agent, because this is a typical example of where it has acted as an oxidizing agent. So this one now has reduced now. It has reduced, this one has oxidized. If something has oxidized, it is a reducing agent. Hydrogen peroxide has been reduced, so it is an oxidizing agent. So what caused the reduction of hydrogen peroxide is this potassium iodide. So the color changed from colorless to brown. This is colorless. Potassium iodide is colorless. But when it has oxidized to iodine, then color of iodine is brown. So reaction has taken place. That is enough reason for us to know that the reaction has taken place. Another examples of oxidizing and reducing agents are this. So for oxidizing agents, oxygen and chlorine are always oxidizing agents because they are electronegative elements. They are always oxidizing agents. Although they are not complex as potassium permanganate and potassium chromate and hydrogen peroxide. While hydrogen, carbon monoxide, and some metals are reducing agents. Metals are always reducing agents. If they are metal in elemental state, they are always reducing agents. Carbon monoxide are always reducing agents because they get oxidized to carbon dioxide. Hydrogen is always a reducing agent. It is either it is oxidized to a water or it is oxidized to another compound with electronegative element being added. So those are just the little concept that we need to understand as far as redox reaction is concerned. So before we go, let us have some quick checklist of what we have learned. Oxidation involves increase in oxidation number. Yes, we have talked about that. Reduction is the decrease in oxidation number because it is the opposite, directly opposite of what we have in oxidation, that is reduction. When there is a change in oxidation state of the element in a compound, the reaction is redox. Yes, direct, simple. If there is a change in oxidation state, even if you don't know any other thing, if you can calculate the oxidation state of each of the elements in a compound from the reactant to the product side, if you see there is anyone that has changed there, even if it is just one, then the reaction is redox. Oxidation state is used to determine how many electrons are lost, gained, or transferred in a reaction or shared in a reaction. Oxidizing agents are compounds that oxidize, that they get reduced rather, while they are oxidizing another compound. So the vice versa is the reducing agent. They are reduced, another substance has got oxidized. And again, to demonstrate that the reaction has changed, color change is one of the properties, is one of the criteria that we use. Don't forget, I think 2 lectures ago, it was on rate of reactions. I said for a reaction to have taken place before we know, some of the things that we use to determine it is either a color change, a change in mass, or if it involves gases, a change in volume, or pressure, as case may be. Because if there is change in volume, there is also change in pressure, if there is any mechanism to measure or change in pressure. So those are the things that have been employed before you can say reaction has taken place. So let us have some exercises to demonstrate what we have learned. The oxidation state of chlorine in this HClO is dash. In calculating this, we want to know that of chlorine. So our first rule is that each of these elements it has oxidation state. That is number 1. Number 2 is that the element in elemental state has oxidation state of 0. So that one is not applicable here. because this is a compound. The number 3 is, in this case now, everything must be summed up to 0. So if we now sum that one up to 0, then we now look at those tables to know the oxidation state of this. Hydrogen is one of the elements whose oxidation state is usually constant, except in some reactions. Usually constant. In a case where the oxidation state of hydrogen is not 1, that means it is with a metal like sodium, like potassium, whose oxidation state is never changed. In that case, the oxidation state of hydrogen will change. But in this case now, hydrogen remains a +1. Oxygen here is one of the elements whose oxidation state is never changed. It is always -2, except in peroxide. So in this case, it is -2. So if we had the oxidation state of hydrogen that is +1 to that of chlorine, I want to determine the plus oxygen that is -2. If we had them together like that, is equal to 0. So we have chlorine to be equal to +1. So the oxidation state of chlorine in this case is +1. In which of the following reactions can the oxidation number of nitrogen be said to have increased? So you calculate the oxidation state of each. In this case, it is +2 because oxygen is -2. So if you calculate that one, you get +2. So if you go like this, -2, so -4. You go here 2, you go here -2, -2, -4. So just calculate each of them like that. You will know which one has increased. Oxidation state of nitrogen changes from +2 to +4. +2 to +4. So that is it. The oxidation state of oxygen in tetraoxide of a cis acid is dash of oxygen. So just write the formula H2SO4. In this case, they have told us the oxidation state of sulfur to be equal to +6. We have known that for hydrogen to be equal to +1. Then we want to determine that of oxygen in this case. So if we apply our rules, also +1, then plus 6, is it +7 or something like that? D +1 +6. So H2SO4. So if we move it to the other side, you have -8 because hydrogen is 2. You put 2 times 1, you get 2. This one is 6. If you add 6 to 2, you get 8. Moving to the other side of the equation, you have -8. Don't forget we have 4 atoms of oxygen. If you divide -8 by 4, you get -2. It is -2. Although without calculation, you should be able to get that is -2 because it is oxygen. Oxygen used to be -2 except in peroxide, and since this compound is not peroxide, oxidation number is equal to -2. So these are some of the questions that you need to just gain time, because this is a very simple one. Some will not be able to finish under 30 seconds. So this one, 5 seconds is enough for you. Having known that the oxygen is usually -2 except in peroxide, just look, is it peroxide? No, then you choose -2 and go away. 5 seconds is okay. You now use your time to do more difficult questions. I think that is what we have to discuss for today. Thank you very much for listening. We are going to another concept, that is electrolysis. That is a very good concept also because the knowledge is acquired, the knowledge is needed, it's useful in metal extraction and electricity generation. So we meet next time by the grace of God on electrolysis. Don't forget that if there is any challenge in our concepts, in the concept we have highlighted, or in any topic we have discussed long ago or not too long, I think from the start of this program, this course, if there is anything that is not understood, maybe I didn't explain very well, or the listener didn't get it very well, feel free to contact us for questions. And if there's anything that is observed that is lacking, or anywhere we need to improve in our lecture, in our videos, so let us try to know so as to correct them in subsequent lectures, because your satisfaction is our concern, and our aim is to pass correct knowledge into young ones so that they should be able to pass it across younger ones also. Thank you very much for listening, and don't forget to share and like our videos.